Thank you, Paul, and thank all of you here and those of you around the world who are joining us this morning. I'm going to try to do this in a way that works both here and remotely. I know I'm supposed to look at the camera, not you. And I don't even see a picture of me, so I don't see what I'm looking at. I'm supposed to see that here. Down in the corner. There we go. Now I can see. So I have to stay here. I can't go out and join you. But so it's a pleasure to be here. Thank you very much for those kind words. And it's a tremendous honor to join the previous Bailey awardees of the Clay Mineral Society. I've known many of the previous Bailey awardees, and it's an amazing feeling to join them and be here today with you to talk about some of the things that I've done in my career. When I was asked to give this plenary lecture, I thought I would try to encapsulate some of the things that I've done in my career, and so that I'm actually going to not talk about the work that I've done on Mars, but one of the themes of my research over the years has been looking at both order and disorder in clay minerals. Paul mentioned the work I did on kaolinite many years ago. That's an example of work on one of the most ordered clay minerals. And so I'll go through that with you today. When I began thinking about this talk, I thought back to when I was a graduate student with Dr. Brindley. Some of you may recognize the young guy in shorts in the middle in the back. There, that's me that's about 1977 when I was a graduate student. That's Dr. Brindley in the middle with a couple of visiting scientists on the right and Sridhar Kurmaneni on the left. So when I remember well, when I joined Dr. Brindley at Penn State, fresh out of undergraduate school, knowing nothing about clay mineralogy, very few undergraduate institutions teach clay mineralogy. My dream was I would find a single crystal of Marilyn, something that looked like this, was nicely ordered, all the layers were together, and with this crystal, I would learn everything we needed to know. I would do single crystal X-ray studies, we would do spectroscopy, and I would answer all of the questions. Well, I quickly realized that was nonsense. That if I had somehow managed to find a single crystal of monmarillinite, a nice sizable thing that you could hold in tweezers and look at under the microscope, the optical microscope, this, what I call unicorn, I think we all know what unicorn is. This unicorn wouldn't have been representative of Smectite at all. And it's something that I as a young student, gradually began to recognize. Maybe many of you know that. If you don't know that, it's important to know. And I gradually learned to recognize that what makes Smectites interesting, useful, valuable, is the fact that they're not ordered. They're not crystals. I'll try to hold it like this so everybody in the internet can see. They're not crystals that are well ordered like this deck of cards. They're like this, as if I threw the cards on the floor. And that's very different physical properties, structure, than the kind of thing. So what would a single crystal of monmarillinite look like? Well, on the left you see, I'm not supposed to use a pointer. So on the left you see a very beautiful vermicular kaolinite crystal. These are from a publication in Impressions Sturges, some wonderful pictures. And what's interesting is this is quite a large crystal of kaolinite. You can see it's not uniform like my deck of cards here, but it's fairly large. On the right are a couple pseudo-hexagonal plates of kaolinite. Look more like something like this, but look at the size, if you can. It's 0.2 micrometers is the scale bar down there. And so, in general, we don't see well-ordered, beautiful single crystals of the kind of thing that you see when you go to a rock shop and you buy crystals. We just don't see that. And what I've been reading lately in the literature about something called quantum crystals. Very interesting things that when you cool them very far, you can they're called quantum crystals because you can't analyze them properly, because by analyzing them, you change them. And it began to occur to me that this presentation is going to have this stuff all morning. It began to occur to me that smectites in particular, and many clay minerals in general, are similar to what you might call quantum crystals, in that by analyzing them, you change them. If a smectite crystal happened to grow as a single crystal in macroscopic, by that I mean 100 or 200 micrometers at least, form in a rock, simply by sampling it or analyzing it, we would change it. And this is partly due to the fact that their structures are so dependent on the surrounding atmosphere. And so it's interesting to think of these as quantum crystals, because anything you do to them is going to change them. If you've ever analyzed clay minerals in the lab, you know you have to be very careful to pay attention to conditions. Instead of using these nice single crystals, we use proxies. And literally almost for 100 years, we've used macroscopic examples like micas, chlorites, dicite, for example. You can find crystals of dicite that you can pick up with tweezers. We've used these to elucidate the structural and physical properties and spectroscopic characteristics of the phyllosilicate clay mineral, or phyllosilicate minerals, and by analogy infer the structures and properties of the clay minerals. It's interesting, we refer to a lot of the work, for example, of Professor Bailey on kaolinites, but I remember well reading his papers when I was a student, and I focused on one here, but even these macroscopic examples are disordered, and I've highlighted this part down at the bottom, where they said all crystals, except for one, showed streaky, which means they showed, get this in the web camera, the crystals had this kind of effect going on. They were not perfect three-dimensionally ordered crystals, even the crystals of Professor Bailey. I remember one paper where they said, we examined 137 crystals and finally found one. Good enough. And I always thought that one crystal is very unique. That's not representative of chloride. So the phyllosilicate clay minerals that are so near and dear to our hearts and in our scientific societies are distinct in a variety of ways. We all know that they have very, very small crystallite size, as I showed you in the SEM photographs. So they have very high surface area. They have layer structures that exhibit stacking disorder. So rather than the deck of cards being perfectly aligned, the rule is that they are disordered or thrown on the floor. For many of them, they exhibit extensive isomorphous substitutions, meaning they're chemical substitutions that cause changes in the structure. Kaolinite and dicite are not examples of that. They're very heterogeneous, structurally, chemically, morphologically, even layer charge. Something we don't often recognize is that smectite layer charge is very heterogeneous. I remember a long time ago talking with Gerhard Legali about smectite layer charge heterogeneity. And I was looking for a homogeneously charged smectite. And I know that he had identified one in one of his studies. And I contacted him and said, can I have some of this material? I would love to study it, to look at the effects of layer charge heterogeneity. He replied saying, oh, well, we only found 0.2 milligrams of this material, and it's the only one we've ever seen in the world. So it's the rule rather than the exception, is heterogeneity. And finally, many of the clay mineral structures have property or have structures that are dependent on relative humidity or partial pressure ratio flow. That's something that I've studied a lot in the lab and also in relation to some of the Martian work. The implications of these variations are profound. And I'm going to focus today on an area that I've spent some of my career working on, namely an X-ray diffraction. And try to use the pointer, I can find it. The diffraction pattern in red is a portion of the powder diffraction pattern The diffraction pattern in red is a portion of the diffraction pattern, powder diffraction pattern for Keokuk kaolinite. And this is one of the few kaolinites in the world that has a crystal structure like the deck of cards right out of the box. And it was that sample that I used to determine the crystal structure of kaolinite and refine the crystal structure. That is three-dimensionally ordered. The blue one is a diffraction pattern of 7 angstrom halloysite, dehydrated halloysite, and that's an example of a completely disordered layer stacking sequence, a kaolinite type material. So that's an example of the disorder. So you see the tremendous variation from three-dimensional order. I've got a picture of me down here. You can see it. Three-dimensional order versus complete turbostratic stacking. In reciprocal space, kaolinite, Keokuk kaolinite is on the left, where we have well-defined reciprocal lattice spots, no smearing. And for halloysite, for example, we have almost continuous, and in some cases, continuous reciprocal lattice rods that have kind of this kind of action going on. They're not constant along C star, and that's a very important thing. So many of you have a background in mineralogy and crystallography, and one of the first things we learn in crystallography is about three-dimensional order. We actually don't learn very much about disorder. We learn about symmetry, and we learn about Miller indices. And from that, we learn about something called the structure factor, which is important whenever we're interested in crystal structures, calculating diffraction patterns, intensities of diffraction peaks. The important thing in this, the structure factor is related to the intensity, but the important thing inside this is that the structure factor is for each individual reflection in an X-ray diffraction pattern. And we define those reflections as based on their HKL values, their Miller indices. What are those? You know, if you took mineralogy, those are integers. They're not 1.0, they're 1. 310, for example. And because they're integers, F is something called a delta function, meaning it has a value at only one place. There's no breadth to it. So at 310, you can calculate F, square it, determine the intensity, and it has a value only there. There's no breadth. How in the world can that apply to a clay mineral diffraction pattern that has broad peaks? Many of you have heard of something called the Rietveld method, which is a method actually first reported in 1969, but really became popular when computers became powerful enough to apply it, that allows us to analyze entire diffraction patterns. And I know many people, I know because I have read the literature, many people apply the Rietveld method to diffraction patterns with very broad peaks. Many people apply the Rietveld method to nanomaterials. Remember what's built inside the Rietveld method. It calculates the intensity at every step, but built inside it is F. And where does F exist? It exists at a delta function. So if you're applying the Rietveld method to a disordered material, to a nanomaterial, you're making huge approximations that you don't even know about. They're in the back of your mind, or maybe not even in your mind. So if we want to now start talking about the structure factor for finite crystals, we need to consider the structure factor over a range of angles. So we have to throw out Miller indices. No longer will we have a value only at the diffraction position. And in the book by Moore and Reynolds, there is a very nice treatment of this, but essentially we just recast the equations using Bragg's law, and we can define a layer structure factor, which normally we call G, and this now is continuous in terms of theta. So we allow it to exist anywhere. Now you might wonder, how do we worry about peaks? The layer structure factor exists everywhere, but we see it only for macroscopic ordered crystals where HK and L are integers. And so we only get to see the layer structure factor right at that one peak position. The peaks are delta functions. This doesn't apply for our disordered materials. And you don't want to use it. So if you're analyzing diffraction data for clay minerals using the Rietveld method, pay attention to what that's doing to your results. Many people say, well, I had a multi-component analysis, the sum was 100%, it must be good. The sum is constrained to be 100%, unless you do some special things. What we now have to do, because we don't just calculate F at the delta function, we now have to consider something called the interference function. And that, the intensity now is this layer structure factor squared, the absolute value of that, times the interference function. Now we can calculate, depending on the crystal size, the diffraction pattern. And there's a wonderful quote in one of Dr. Brindley's books by W.F. Bradley, a renowned clay mineralogist of the mid-20th century. He said, the interference function is the window through which we view the Fourier transform, through which we get to view G. Remember that, it's a very insightful comment, and it will bring home to you that you need to worry about peak breadth. If we don't have a tiny crystal, if we have a crystal like this deck of cards, we can ignore that. But here's the interference function, and it's not particularly important to worry about the details, but you can see that it's related to the number of unit cells times the repeat distance divided by this. And so this n times d is actually the crystallite size. If you calculate the interference function for 1 unit cell, we don't get diffraction, and the phi is at 1 at all angles. For example, with an n value, 100 unit cell repeat, which is actually twice the number of layers in this deck of cards about, phi becomes pretty sharp. Remember, it's the window through which we get to view G. Here's an example of the interference function calculated for a d of 10 angstrom, which just determines where that center point is, and n of 50, which determines how broad the window is. Remember, that's our window. You can see here from 0 to 32 theta, the interference function is fairly sharp. Remember, it's our window. We only get to see intensity, or G squared, right under this peak. G exists out here in this region, but we don't get to see it. Here's an N of 20. 20 of well-ordered clay mineral with 20 repeat units would be pretty nice clay mineral. That's an N of 20. 10, the full width at half maximum on the peak at about 9 degrees is almost 1 degree 2 theta. That's our window. We get to see G from here all the way over to here. If we worried about F, we would only know what it was right in the very center of the peak. So for those of you here, F would be right in the very middle of the peak, the delta function. We wouldn't get to see all of the other stuff around the side. There's an N of 5, full width half max is twice, and then an N of 2. So keep in mind, that's the window. That's where we get to peek through that and see G. And you say, well, no problem. G's probably, we know what G is because we can calculate. No, we know what F is. We can calculate F right there. G isn't constant across there necessarily. And that's what makes interpretation of powder diffraction patterns of fine-grained materials in general difficult. Brindley and Robinson, more than 50 years ago, had a very, very nice paper on halloysite, and they showed the variation of G squared with angle for halloysite. And here you can see 0211. You're familiar with the asymmetrical 0211 band for Smectite, for Kaolinite. Interestingly, G is approximately constant across that peak. Look at the G squared for 06, for the 06 band. It's very much not constant. And when you apply, there's a geometrical factor that Brindley talked about. For 0211, it's shaped like this. if you multiply this factor by an approximately constant O2 G squared, you get the nice asymmetric diffraction band that we see for the O211 band for phyllosilicates. What does that mean? Well, first of all, it means that you don't look at the broad band at about 60 to 62 degrees with copper radiation for phyllosilicates and call it O60. That's HKL. That's three-dimensionally ordered crystals. That is not a three-dimensionally ordered crystal if you have two-dimensional diffraction bands. It's the O6L band. So you can't measure the center of the O6L band and conclude that that is O60, because if G squared and the geometrical factor are asymmetric, the peak can effectively move. So the centroid of the peak is not where 060 would be. So try not to do that. Everybody does it, but you shouldn't. The other thing is, remember, the Rietveld method uses HKL, integer values. Be very careful. There are a couple of approaches that have been devised in the last 10, perhaps 10 years. BGMN is one of them by some of the members of the audience, and they more correctly treat these issues. But don't use an off-the-shelf Rietveld program and plug in delta functions for broad asymmetric peaks. Finally, don't think that, oh, I can broaden my diffraction peaks if I put a series of split Pearson 7 peaks. I can fit my diffraction pattern. You can fit it. What does it mean? It doesn't mean much. So don't fool yourself that just because you can fit your diffraction pattern with the Rietveld method, that the information that you get is accurate or real. So what we and a number of other people have begun doing is using methods that don't rely on three-dimensional order. And what I have begun doing, mainly with a recent postdoc of mine, Alberto Leonardi, who is now in the UK, is using something called the Debye scattering equation. And that is not based on the assumption of three-dimensional order. The Debye scattering equation, this is for you, for those of you out on the web, this is for, the test will be later. But really, if you look at this, you'll see that it's very similar to the very popular PDF approach that people use today, pair distribution function approach. Essentially, you worry about the atom pair distances. With this method, you cannot use symmetry to expand your crystal. You have to define the positions of every atom in your fake crystal on the computer. Every single atom in space. So it becomes a very large job. And it's only been until recently that this approach has been used a lot because of the amount of computing power that it takes. And we did these simulations at my university. We have one of the top 10 in the world supercomputers. And my postdoc was the #1 user on this for 2 years. They congratulate. So you can start these simulations and they'll run for a week on a supercomputer. And what we do is we can easily compute the layer structure within the layer. That's constant, fortunately, for our two-dimensional material. So we know the structure fairly well within one sheet. But we don't know from the next to the next. And so we then have to construct models of different types of disorder. And for the turbostratic case, we use one individual layer structure, and then we have different types of disorder going from one layer to the next. We can speed it up by doing that, but it's still relatively slow. So I'm going to show you some examples of the results. These are kind of hot off the press kinds of things that Alberto has just finished recently. And it's been quite exciting because he's been able to combine his simulations, his structural simulations, with molecular dynamics simulations and calculations of the energy. So he uses molecular dynamics with Randy Seigen's clay FF, clay force field. And comes up with an energy. What we do is we create this atomistic model that I mentioned to you, and then we use just 2-layer crystallites, calculate the energy without defects, so a perfect crystal, and then we calculate the energy with a defect, and we can see the energetic effect of that particular type of defect. And in this case, we looked at increasing the interlayer spacing. So we had a model with 2 layers, and we gradually increased or decreased the layer spacing. And you can see, fortunately, the equilibrium spacing is about the lowest energy. So it gives us some insight. Then we did Debye scattering equations. We started with the real structure, and for kaolinite, we used the refined structure that I did in the 1980s. We disordered it. We used a 12-layer, 50 nanometer diameter crystallite. If we went any larger, rather than 2 weeks on the supercomputer, it would be 2 months. The time goes up drastically because you calculate. Remember, you have to identify every single atom. You can't use symmetry from one unit cell to the next to the next. You have to define them all. We made 100 independent models, statistically different, but with the same type of disorder. And then Alberto did the Debye scattering equation simulation and calculated the diffraction pattern. And you can see here in the upper left are the diffraction patterns for different kinds of XY shifts. This is basically what you might call indentation. A perfect crystal is down here outlined in red. And then we started shifting the layers like so and calculated the effects of that. And so for different kinds of XY shifts, you see gradually we go from a diffraction pattern that resembles that of Keokuk kaolinite to something that becomes increasingly more turbostratic. Here we looked at layer structure misorientation in terms of orientation. And here we have different kinds of rotations. We have uniform random, which is turbostratic. We have ideal single crystal, which is essentially the Keokuk kaolinite diffraction pattern. And at the same time, we calculated the energy for all of these different configurations. And you can see, interestingly, that red is bad and blue is good on this curve here and here. And you can see that there are certain types of rotational disorder that are favorable and certain types that are very unfavorable. And so we now can get insight into which types of disorder we might see. In the past, Brindley proposed a few, Planson and Jafar proposed some, and now we can, going 360 degrees around, this was a lot of calculations, and we can see where some are not so good and some are good. And now we look at layer structure shift. So just shifting the layers relative to one another, like in this model up here in the upper right, with a random shift here, the ideal single crystal again would be like Keokuk, and then we have these different interlayer shifts. And here, look at this. There are definitely some interlayer shifts that are favored, they're energetically favored, and there are some that are most definitely not favored. You would never expect to get those. So we're able to identify the kinds of disorder we will expect energetically. Now we're not just matching our simulations with our diffraction patterns and saying there's a good match. A good match doesn't prove that it's right. But when you can add to that energy calculations, then you start to get a better idea that these are real, showing you real results. This is the B/3 of Brindley and Robinson. And again, this plot's the same. And these are the simulations. So you can see how the diffraction patterns change in this so-called O2-11 region, going from something like Kaolinite, three-dimensionally ordered, to turbostratic, as you add in these plus or minus B over 3, or what Bob Noonan suggested, just plus B over 3. This is the octahedral vacancies, Alain-Plançon, and again, we can see the effects of those in the diffraction patterns, contrast those with Noonan. So you begin to look at the disorder landscape and get an idea of what you can get out of your diffraction patterns, and do those make any sense energetically. So we can now put all of these calculations, we have hundreds of calculations representing probably months of computer time, and we can start to compare those with some of our data. We've measured some, we have lots of diffraction data for Kaolinite, but just showing you KGA2, KGA1, and API 9, and we can look at the characteristic layer size, and you can see we're on the order of 20 to 50 layer repeats, but there are defects within those, and we can start to model the diffraction patterns, and the pointer is very slow. We can model the diffraction patterns and use the different features of these two-dimensional bands to extract the kinds of information on the kinds of disorder our real samples have. We use that plot in the, there, good. So at the top are some laboratory data. At the bottom are synchrotron data. My postdoc wanted to get carried away and he measured synchrotron data. The interesting thing is there's so much broadening due to the specimen in your diffraction experiment that going to a synchrotron really doesn't gain you anything significant. If you need high resolution, you don't normally need high resolution when you have a sample that is very disordered. So we were able to get information on these. The average layer diameter for these, API 9, as many of you know, is a quite a nicely ordered Kaolinite. KGA2 is not as well ordered. The standard deviation is, the average standard deviation is small for KGA2. Indentation percentages, the structure shifts, stacking faults. So the major type of disorder in these clays was stacking faults, not, for example, indentation. So we were able to really characterize from the different unique spots in the diffraction pattern the types of disorder in these clays. And what we really ended up then with was beginning to think about whether or not these types of disorder that we see in real clay samples can shed any insight onto formation mechanisms. You might expect a clay that crystallizes slowly in a geode, like the Kaolinite, to have a degree of disorder different than one that forms in a soil, different from one that forms or that you find in a stream that has suffered a lot of mechanical abrasion, a lot of mechanical activity that has caused shifting of the layers. So we're beginning now just to think about, can these energy calculations shed any light into the mechanisms of formation of these disorders? If any of you is lucky enough to have ever worked with Kaolinite and you happen to put it in your mortar and pestle and grind it, you will find that you destroy it. Well, you affect the layer stacking order tremendously. And so it's very easy to cause changes in the layer stacking order. You can imagine if you extract something from a soil that formed in situ, it would never have had any mechanical effects of the sort that you might find in a river sediment. And here's the disorder energy. This is the bulk for an infinite perfect crystal, the isolated layer energy. This is one single layer, and this is a single crystal with a finite size of the sort that we modeled. And we can see that the lowest energy is the API 9, KGA, and KGA2 is higher energy, and these are other virtual kaolinites that we made. So they're all higher energy, less stable than Keokuk kaolinite, for example. So just a few concluding remarks and some notes for those of you on the internet so you can read about it. Just remember that the fine-grained nature of clay minerals, the fact that they're disordered, means that we don't have three-dimensional order. And we can't use all of the crystallography that assumes that HK and L are integers and our diffraction peaks are delta functions. So don't be careful applying the Rietveld method. I know if you're using the Rietveld method, you're all going to go back and use it and say, Dave told me not to do it, but it looks pretty good. And it will look pretty good. The question is, what does it mean? And just remember, even if you can fit it, you can broaden the peaks. There are all kinds of ways with the Rietveld method to broaden peaks. The fact that you can fit it doesn't mean it means anything. Probably it doesn't mean it. And using approaches like the Debye scattering equation, I think is the way to go in the future, particularly now that we have faster and faster computers. Probably in 10 years, there'll be young people in the audience who will be doing this routinely on their desktop. Right now, it's reasonably difficult. We've just a little bit on the energy. As I said, we are hopeful that we may be able to get insight into the source of the disorder. So might be able to distinguish between different creation mechanisms. And just what I've always marveled at, the factors that make clay minerals difficult to study, and there are a lot of factors. They're fine-grained nature, they're heterogeneous, they're disordered. For me, in much of my career, that's been really a source of major excitement for me, and I know for many other people. It's some of the most exciting materials that we have to work on. Thank you again for the honor of presenting the